In Unit 1, we have learned how force affects the state of motion of bodies. Force can also make the system equilibrium, just like what we have learned in Unit 3. In this unit, we will investigate the direct effect of force in the body itself. We will study an important property of solids, called elasticity. And we will see that forces can cause deformation on solids when stress is applied to it. Good luck on your next journey and just enjoy learning. Before we discuss in detail the elasticity of solids, let us make some review on the states of matter you have learned during your senior high school days. We learned the basic states of matter such as gas, liquid and solid. A gas is a matter composed of atoms or molecules that moves through space as free particles. It has no definite shape and requires a container to form a shape. This figure shows a comparison between two plastic bags, in which one is inflated. As you can see, the amount of air inside assumes the shape of the plastic. Gas is also treated as a fluid because it has the ability to flow. In this video, we see that the air flowing from the blades of this electric fan causes the paper to float, indicating that air, which is a gas, has the ability to flow. It is also compressible, which means that its volume can be changed, either compressed or expanded. In this video, this syringe contains 3 milliliters of air. If we close the inlet section of the syringe with our index finger, and we apply a compressing force on the piston, we see that the air is compressed to about 1.5 milliliters, that is compressed to half of its initial volume. Since gases can flow, they are considered as fluids. We will return to idea in Unit 5. Another state of matter is liquid. Like gas, liquid has indefinite shape because it also requires container to form its shape. This figure shows amount of water in 3 containers in different shapes. Liquid has also the ability to flow, therefore, liquids are considered fluids. In this video, we see that water flows from one container to another by means of gravity. Contrary to gas, most liquids are nearly incompressible. It has almost fixed or definite amount of volume. In this figure, we see a syringe filled with 3 milliliters of water. Notice that if we try to compress it by exerting a force on the piston, it is almost motionless, indicating that water is nearly incompressible. And since that liquids can flow, they are also considered as fluids, and we will include the study of liquids in more detail in Unit 5. Next important phase of matter, which we are focused with, is solid. A solid is a state of matter having definite volume and shape. Unlike gas and liquid, a solid does not require a container to define its shape. Like liquids, solids are nearly incompressible. However, in some cases, solids can be deformed slightly, upon application of forces. This figure shows solids, like 3D printed object and wooden cubes, that do not require container to define its shape. No matter how careful we are in classifying phases of matter, we cannot classify fully the state of a matter solely into solid, liquid or gas. The state of certain substance depends on its temperature. For example, water can be solid ice, liquid water, or gas or steam. Another example is matter and stars, which does not fall into the solid-liquid gas classification. Stars consist of ionized atoms called plasma. Lightning is an example of plasma present on Earth. The rice we eat are cereal grains. The grains of granular media are considered solids, but the macroscopic properties can be considered closer to liquids, because they can flow like liquids. A glass is another state of matter. It is neither a liquid nor a solid. Glasses seem to be solids, but it can also be viewed as liquids, with extremely high viscosity. Other states of matter are foams, gels, and Bose-Einstein condensates, which are currently receiving a lot of interest from scientists and researchers. Here we have your 8X form mattress we use to have comfort sleep at night. While the hair styling gel most of the boys are using is actually a form of gel. Finally, our body, Plants and animals consist of biological tissues, which predominantly consist of water, able to keep or change in shape depending on environmental conditions. Now, we investigate the main topic of this course unit. In this section, you're gonna learn important concept regarding the elastic properties of solids. We mentioned earlier that solid bodies can be deformed. It is possible for a solid to change its shape or size, or both, with the application of external forces. When the forces are removed, the object tends to return to its original or normal shape. This ability of solid is called elasticity. For example, a rubber band will resume to its normal length after being stretched by means of a small amount of force. When force is applied, the body is said to be stressed. Stress S is a quantity that is proportional to the force causing a deformation. More specifically, stress is the external force acting on an object per unit cross-sectional area A. The amount of deformation of solids differ according to the type of material. The measure of the degree of deformation is called strain, denoted by Greek lunate, epsilon. Experiment shows that for sufficiently small amount of stress, stress is proportional to strain. This proportionality relationship is associated with a constant called elastic modulus. The elastic modulus is therefore defined as the ratio of the stress to the resulting strain. For the purposes of this unit, we shall consider three types of elastic moduli for different types of deformation: Young's modulus, shear modulus, and bulk modulus. Young's modulus measures the resistance of a solid to a change in its length. Shear modulus measures the resistance to motion of the planes within a solid parallel to each other, while bulk modulus measures the resistance of solids or liquids to changes in their volume. We shall discuss these one by one in more detail in succeeding sections. The first type of deformation that we are going to discuss is the change in length of a solid, when an external force is applied. Consider a bar with an initial length L sub I, and cross-sectional area A, that is held secure or clamped, at one end. When an external force F is applied perpendicular to the cross-section, internal molecular forces in the bar resist distortion. The bar reaches an equilibrium situation, in which its final length L sub F is greater than the initial length, and the external force is exactly balanced by the internal forces. We see that, at equilibrium condition, the bar is stretched or deformed by delta L. We define the tensile stress, denoted by letter S, as the ratio of the magnitude of the external force F to the cross-sectional area A, where the cross-section is perpendicular to the force. The SI unit of tensile stress is Newton per square meter, as long as the unit of force is in newtons, and the area is in square meter. In honor of French mathematician Blaise Pascal, Newton per square meter is also Pascal. We learned earlier that the quantity called strain measure the degree of deformation of a solid. Now, if a solid is subjected into a tensile stress, it can cause tensile strain on it. In this case, the tensile strain, denoted by the Greek lunate epsilon, is defined as the ratio of the change in length delta L to the original length L sub I. Basically, strain has no unit, since it is a ratio of two linear dimension, for as long as the change in length or deformation. We have discussed a while ago that stress is proportional with strain. With this, the tensile stress and strain are directly proportional. Again, this proportional relationship is defined by the constant property of solid called Young's modulus. It is a property that measures the resistance of a solid to a change in its length. We define Young's modulus Y by a combination of the ratio, tensile stress and tensile strain. The unit of Young's modulus is the same as the unit of the tensile stress, and in SI system, it is expressed in pascals. Young's modulus is an indicator of the degree of elasticity solids. The table below shows accepted values of Young's modulus for different substances. From this table, we see that steel is more elastic than copper. It is a misconception to say that rubber is more elastic than steel. In fact, rubber is very less elastic than steel. Steel has more capable of returning to its initial length when subjected to stress than rubber. Although rubber is stretchable, it is almost incapable of returning to its initial length when subjected to large stress. If we apply the equations for stress, force over area, and strain, deformation delta L, over the initial length, we can derive for an equation that defines change in length, or deformation as the force F, multiplied by the initial length L sub I, divided by the product of its cross-sectional area and its Young's modulus. We have learned that deformation occurs on a solid body when stress is imposed on it. For relatively small stresses, the bar returns to its initial length when the force is removed. When we increase the stress for such, it will no longer return to its initial length. The solid body has already reached its elastic limit. The elastic limit of a substance is defined as the maximum stress that can be applied to the substance before it becomes permanently deformed, and does not return to its initial length. Any additional stress will cause permanent deformation on the body. A stress versus strain curve is used to visualize this elastic behavior of a material. Initially, the curve is a straight line, with a slope equivalent to value of Young's modulus of the materials. Here, we see that elastic limit is around 350 megapascals. This is the maximum stress that can be applied, without causing any permanent deformation on the body. Any additional stress from this limit, the curve will deviate from straight line to almost horizontal line, which causes permanent elongation or deformation. The cross-sectional area becomes smaller and smaller, called necking, until the body ultimately breaks. The value of stress at the breaking point is called ultimate stress. In this case, the ultimate stress for this material is around 440 megapascals. At this point, the material is broken. Now, let us give a sample problem. Problem number 1. Assume that Young's modulus for bone is 1.5 times 10 raised to 10 pascals. The bone breaks if stress greater than 1.5 times 10 raised to 8 pascals is imposed on it. Letter A. What is the maximum force that can be exerted on the femur bone in the leg, if it has a minimum effective diameter of 2.5 centimeters? Letter B. If this much force is applied compressively, by how much does the 25 centimeter long bone shorten? So imagine this is the femur bone, and it has Young's modulus of elasticity of 1.5 times 10 raised to 10 pascals. And it will break with a stress of 1.5 times 10 raised to 8 pascals. The diameter of the bone is 2.5 centimeters and its initial length is 25 centimeters or 0.25 meter. What we are looking for is, letter A, the maximum force that can be exerted, and letter B, the change in length of the femur bone, delta L. Now, we solve the problem. For maximum force, we begin with the formula of stress, force over area, and the cross-sectional area of the bone, assumed circular, is pi over 4, d squared. Using these two equations simultaneously, we see that the maximum force is equal to the product of stress, times this cross-sectional area pi over 4, d squared. Substituting the values. So the maximum force is 73,631 newtons. For letter B, the change in length delta L, we will use the formula of strain, change in length divided by the initial length, as well as the formula of stress, Young's modulus times the strain. Again, using these two equations simultaneously, so the change in length is the product of stress and the initial length, divided by the Young modulus. Substituting the values will give a change in length of 0.0025 meter, or that is 2.5 millimeter. We see that, if we exert a force greater than this value, the bone will surely break. This is the reason why that when we jump from a certain height, we must bend our knees in order to reduce the force due to impact.